Hi everyone, and welcome to the histamine detection in tuna using hyperspectral imaging webinar. My name is Marissa DuPont. I am the marketing specialist. This webinar is being recorded and should be available for viewing within 48 hours. We will answer as many of your questions live as possible. Additional questions will be answered by email after the conclusion of this webinar, and you can send questions to marketing@headwallphotonics.com. If you have questions, please use the questions panel in your GoToWebinar control panel on your PC or phone. You can see where those are located on your screen. Now I'd like to introduce our panelists, William Rock, PhD, who is Applications Manager here at Headwall, and George Killian, who is Applications Scientist here at Headwall. And now I will turn it over to Will.
All right, thank you very much for the introduction, Marissa. So I'd like to start off this webinar with a brief introduction to Headwall Photonics. Headwall Photonics has been in business since 2003 and was recently acquired by Arsenal Capital Partners. We're headquartered in Bolton, Massachusetts, and we have 2 other locations in Massachusetts and another location in the Netherlands. Headwall Photonics employs around 100 highly skilled employees and is ISO 9001 certified. Across the different sites, Headwall has around 40,000 square feet of engineering and manufacturing facilities, and we serve a large global customer base across our core markets. And we serve 3 product groups serve these core markets that I will go over on the next slide. So the 3 main business areas that Headwall serves are machine vision, remote sensing, and optical components and assemblies. Headwall is a leading supplier of hyperspectral imaging solutions used for machine vision and remote sensing applications. And Headwall specializes in manufacturing optical components and assemblies, such as diffraction gratings, spectrometers, and spectrographs that are sold to OEMs or to end users. So the machine vision product line, which is the main focus of this webinar because we're focusing on a machine vision application in the histamine detection of tuna, it includes hyperspectral systems and software that are sold to emerging industrial automation applications like food processing, healthcare, and to the consumer market. Then our remote sensing and our remote sensing products are generally sold for spectral classifications of objects, materials, and natural formations in applications that are including earth monitoring, agriculture, and mining. So just briefly about our remote sensing product lines, those can be sold as airborne hyperspectral payloads that can be integrated by the end user onto either a drone or a manned aircraft. And Headwall also sells turnkey UAV hyperspectral packages that can be unboxed and flown to collect hyperspectral data the day they arrive on your doorstep. And that's, of course, our recommended path to go is to let Headwall take care of all the fuss for you and give you a package that can be unboxed and used on day 1. Other optical components and assemblies products include holographics replicated gratings, waveguides, and micro lens arrays. So now we're going to go over in a little more detail on our machine vision product line. As you can see on this slide, here are 3 examples of machine vision products. On the far left, you can see the MVC V-Near, which is the smallest and lightest sensor in its class. It covers what we call the V-Near or visible near-infrared spectral range, spanning 400 to 1,000 nanometers. It provides high spatial and spectral resolution, USB 3.1 connectivity. And so this sensor is sold generally along with our computing and software packages to give you a full end-to-end solution. In the middle, you can see Headwall's HyperSpec MVC Near, which is a near solution, and Headwall defines the near-infrared spectral range as 900 to 1,700 nanometers. And this is an affordable solution, especially designed for machine vision applications requiring the near infrared spectral range. It comes with gigabit Ethernet connectivity and also has a small form factor. And on the far right, you can see our award-winning Veneer hyperspectral imaging system. So the MVX provides hyperspectral imaging and onboard processing all in one box. And the box also comes with ingress protection to help for easy deployment in challenging environments. So a few of the key applications that can be addressed using hyperspectral imaging for machine vision include color consistency, nut sorting, meat grading, and fruit grading. And so this table will show you the products that are most applicable to those different applications, and in general, what is desired by those different applications as well. So for color consistency measurements, generally a COTS product is used and can be used for QA, QC, or quality assurance measurements that can help ensure that the color of your product line remains consistent. The nut sorting application, you can see a real example of a deployed nut sorting application if you visit our website. And so this is a common use for hyperspectral imaging because hyperspectral imaging can allow you to differentiate very similar looking items such as nuts and shells and other common foreign materials seen in nuts such as barks and sticks and twigs and things that can be hard to differentiate from the good nut product in using just a standard RGB camera. Meat grading is another powerful application for hyperspectral imaging. A great example of that you'll see in detail later with the grading or histamine detection on tuna. It can also be used for things like fat to lean measurements or grading of other meat products as well. And fruit grading is another application that hyperspectral imaging can be deployed for as well. Including measurements of the ripeness of fruit, detection of softness or bruising in fruit that might not be visible to the naked eye or to an RGB camera, or also the non-contact prediction of the sweetness of fruit, or which is commonly referred to as the measurement of the brix. So now I would like to hand over the floor to my colleague George, who will give you a brief introduction to hyperspectral imaging so you have some background before we dive into the tuna application.
Thanks, Will. So for those that are unfamiliar with hyperspectral imaging, allow me to give you just a quick explanation and how it can be applied for machine vision. First, hyperspectral imaging combines the spatial information that we get from a regular image with a chemical discrimination of spectroscopy. It creates a powerful measurement technique. Hyperspectral imaging sensors such as the MVX and MVC Veneer we mentioned earlier gathers information from over hundreds of spectral bands for each spatial pixel in the image, and that data is stored in a data cube. If you consider the image on the left of your screen of the parrots, the hyperspectral image of the same scene would return a stack of images for each wavelength within that range, creating the data cube. Hyperspectral imaging offers an advantage over multispectral imaging of the same scene because it gives us a wider range of the spectral pattern of each of the different pixels within that image. Now, there are lots of different types of hyperspectral imagers. Headwall utilizes a push broom sensor or a line scanner. So how do our sensors collect that information? Well, if we imagine we're flying a drone over a coastline like the image on the left, a snapshot camera of that scene would simply collect a 2D array with columns and rows of the pixels within that scene. Our push broom line scanners collect a thin line of pixels and move across the scene, building that image step by step. For machine vision, we do the same thing. Instead of moving the sensor over the scene, we move the scene beneath the sensor, where we collect a line and line of pixels of the object beneath. In this case, it might be tuna, or then we build all of those pixels together to get the overall spectral pattern of the scene beneath. And then we can take all that great data, capture it, analyze it, and create a classification model or other different kinds of models that we can employ on the line. So hopefully that gave you a little bit better understanding of hyperspectral imaging, and I'll pass it back to Will so he can go into the tuna histamine study that we did here at Headwall.
All right, thank you very much, George. So I'd like to start off the section on the tuna histamine study with a brief motivation for why it's important to measure the histamine levels in certain fish, including tuna. So when histamine is present on tuna, it can cause illness, and it is a toxin that is produced by bacteria on the surface of the fish. So this toxin can't be cooked away from the fish. So once it's there, it's going to make you sick. And so it's very important to not allow the toxin to develop on the fish. And in most cases, the toxin develops because the fish isn't properly stored. So like most bacteria, its growth is promoted in temperatures, in warmer, say, closer to room temperature environments, and it really increases if you warm the room up to like 90 Fahrenheit or say 30 C or so. So it's very important to store the fish properly to prevent the formation of histamine. And once the histamine is there, you can't just cook it away. And so it's very important to be able to measure and ensure that you have high quality fish and that those fish don't have illness-causing histamine toxin on them. The FDA also advises that the formation of histamine can and often is non-uniform throughout the entire piece of fish. And so they actually give some guidelines on where you should sample the fish when you're measuring the histamine level, because all of the standard protocols used to measure histamine include spot samples. So you take a little chunk of the histamine off of it, you move it to a laboratory, you do some chemical tests on that piece of tuna that, of course, and then you're only getting a histamine measurement for one spot, and you're destroying the sample that you're getting the histamine measurement from. So those are, that is the accepted way to measure tuna histamine. And those are all things that could be improved with hyperspectral imaging that could provide a non-destructive and all-inclusive measurement of the histamine level on the surface of the tuna. So briefly, what did we do in this tuna histamine study? So 15 raw tuna steaks were measured using a Headwall Veneer hyperspectral imaging sensor on a scanning stage. So this is much like the image that George showed on the previous slide. We had tuna steaks passing underneath the sensor, gathering the full Veneer hyperspectral data. Veneer is, again, visible in infrared, covering 400 to 1,000 nanometers. The histamine levels were measured on 7 of those 15 tuna steaks using a Neogen Veritox assay. Or again, like I briefly explained before, a spot sample was taken from the tuna. So some of the tuna was cut off, taken back to a laboratory, and run through this standard assay to get a prediction level for of the histamine parts per million on that piece of tuna. Some of the, just a little bit of bookkeeping, some of the larger tuna steaks required 2 scans because they were quite big. So that's why when I show some of the data scans later, you'll see some of them broken into 2, or you'll see maybe more dots on my graph than the 7. Also another bit of bookkeeping, the histamine or a histamine regression model was built using the perClass Mira software package. And so over the next set of slides, I will give you a brief summary of how that model was built. But to avoid burying the lead, these are the results of that model. So the plot that I'm showing here is a plot of the predicted histamine value versus the measured histamine value. So a perfect model would fall perfectly along that black line, so it just would form a perfect line there. But this plot demonstrates that there is absolutely a correlation that we can measure between the venier hyperspectral data and the measured histamine value on the tuna. So there's some important nuance in that language that I used, a correlation. So hyperspectral imaging is an indirect measurement technique, meaning that there's nothing inherent about the hyperspectral data that says this is the absolute measure of the histamine. We need to train it with known ground truth methods that can directly measure the histamine content, such as the assays that were used. So we are correlating spectral signatures to known measured histamine values. This particular model is also just a demonstration of what could be done, and was done on a fairly small sample size. So you can see there are 9 dots on the graph generated from 7 different tuna steaks, and there were 9 dots on the graph because some of the very large tunas were measured in 2 pieces, and so they were 2 different tuna objects. And also the robustness and of this model should be tested with a larger data set that is not included in the model development. And Headwall would be very excited to work with a motivated partner to develop a robust and deployable solution if the real-time screening of the histamine level on tuna interests you. Please contact us, and we'd be excited to work with you. So how is a regression model built using the perClass Mira software, and more specifically, how did we build this tuna histamine level regression model? And so before I get into my explanation here, I just want to also note that if you want more detailed explanations or to see more of the features that can be deployed using perClass Mira, please visit their website, perclass.com, and they have a whole series of training and tutorial videos that you can peruse at your leisure to get more details and, again, see a wider variety of different applications. So a regression model is built through a series of steps. The first step is to create a classification model, which will assign a class to every spatial pixel in your image. So I always use the language spatial pixel and spectral pixel because we're creating a hyperspectral data cube where in one axis you have all of your spatial information, in the other axis you have your spectral information. So that's just the common language that we often use, is talking about a spatial pixel is just one spot on that image, and a spectral pixel would be the intensity at one spectral value, or I could often talk about the spectrum at a single spatial pixel. So the first step is to produce a classification where we group every spatial pixel into a certain class. In this particular model, we created a 4-class model where in the dark blue you see the background. So of course we don't want to include the belt in our model, and so that's classified as a background signal. There's the tuna, which we're actually using to build our regression model on. And then there are a couple of other classes that appear on the tuna that we want to exclude from our regression modeling, that are some of the shadowed pieces at the side, and also the marbled, the fat bit in the tuna. And some of the gray pixels that you might see in there are unclassified pixels. And so I did not include that in the color key. But the unclassified pixels include things like glare, where the spectral data is not as reliable when you're getting glare pixels back into the sensor, and so those are excluded from the regression model as well. So again, step 1 is build the classification model. From the classification model, and we recognize objects, and from the objects, we will build a regression model. And so again, on this first slide, we can see an RGB image on the left and a per pixel classification on the right. And in that per pixel classification, every single pixel in the image is assigned to a class, either background, tuna, shadow, or fat. And you see that -F on the tuna. That means the tuna is the only class that is placed into the foreground, meaning that is the only class that an object is formed from. And so I'll talk a little bit more about objects on the next slide. So on these two images, on the left, you see the per pixel classification image from the previous slide. And on the right, you see the object image. So after we identify every pixel in the scene, or after we classify every pixel in the scene, we will separate groups of classified pixels into objects. So a contiguous area of pixels classified as tuna will be recognized as a tuna object. I might interchangeably use the word tuna steak, because essentially what I want to do is build an algorithm that first finds the tuna steak. And once you find the tuna steak, you can assign a regression value to that tuna steak. So by default, perClass Mira regression models operate on the object level. So that means you will find objects in your data stream. So if you have a whole bunch of tuna steaks moving by in your conveyor belt, every time a tuna would pass under your sensor, you would recognize it as an object, and then your regression model would assign a regression value to that entire tuna object. And so each object would get one regression value, representing the average histamine content for that entire tuna steak. And so again, that is the standard way to deploy a regression model in perClass Mira. So on the next slide, I will show some pretty neat images that can be generated by these regression models as well. So again, it's important to note that when you're deploying a regression model, the standard way is to produce one regression value per object. Another accessible output is the per pixel regression values. So this can provide a heat map of the predicted histamine value on a given tuna steak. And so in this case, I showed one heat map from what ended up being a medium histamine level piece of tuna, and another heat map from a tuna that had a high histamine content. And so on the far right, you can see my color scale that goes from 0 ppm is the dark purple, and 200 ppm is the bright yellow. And so that can orient you a little bit on what this image looks like. And so this is just demonstrating that you could return a heat map of the estimated regression values across the whole tuna steak if you are worried about finding hotspots on a given tuna. But again, the standard mode of deployment is to get an average regression value for each whole piece of tuna that would allow you to screen every piece of tuna instantly as it's passing under your belt to get its histamine content. So now if we could go on to the next slide. Okay, thank you. So how do you go from training a model, like I went over previously, the steps for training a regression model are create a classifier, segment out objects from that classifier, assign regression values to the objects in that classifier. And so that's all depicted by the left image, going from collecting the training data, downloading the data, and creating the model. And then the right image shows a cartoon of deploying that. So after you've created a model, it can be deployed on a product like the MDX that has real-time processing, where as the tuna or whatever your product is passing underneath the hyperspectral imager, the classification model is working in real time and outputting results again instantly that can either be sent to something like a picking robot. So say you wanted to eject the bad tuna, you can send the information to a robot to pick it, or to a database with the cloud or somewhere. So say your goal was to separate the tuna or grade the tuna based on the histamine level. You could just record the data somewhere to allow you to assign a grade or a value to the tuna as it goes down the line. And of course, you can visualize how this could be used for other applications. If your application is to detect foreign materials from your product line, you could send the location of the foreign materials to the picking robot, and it could pick the foreign materials out as well. Some of the big advantages, especially in the case of tuna histamine, is this would provide you instant and rapid instant feedback to allow you to enact rapid corrective action. So rather than taking a chunk out of your tuna, taking it back to a lab, running an assay, and then getting a result, you can get instant feedback on the predicted histamine level in your tuna. And if you're all of a sudden getting a bunch of tuna that's measuring high histamine content, you can rapidly correct your process, find the root cause of these elevated histamine levels, and fix it without delay. Another big advantage is that it allows 100% screening to help eliminate 100%, I should be careful and say surface screening, because hyperspectral imaging is a surface measurement of the product line to avoid errors that come about due to spot sampling. So just taking a small bit of tuna from a subset of the tuna steaks that are going down the line. Instead, hyperspectral imaging would allow you to image the full product line as it is going by. To summarize again, this tuna histamine application, we were able to see in our initial studies a correlation between the V-near hyperspectral data and histamine levels on raw tuna. Now, these initial tests are very promising, but of course, more data is needed to determine the robustness of this model. perClass Mira software was used to create the regression models here. If you want to know more about the perClass Mira software and other ways to apply it, please visit the website perclass.com. This model could be used to predict histamine levels on raw tuna in real time as they're passing under the sensor on a conveyor. And again, to reiterate, Headwall will be very excited to work with a partner to develop a real solution to screen a raw tuna for histamine content to help both guarantee the quality of tuna and keep consumers safe. And with that, we're going to continue on with a short demonstration showing how we go from collecting raw data to training the raw data in perClass Mira to deploying a classification model, all within the same software package. So a very seamless transition from data collection to data training to model deployment via the perClass Mira software package. And so please enjoy this short demonstration.
Thanks, Will. Now that you've seen how to build a regression model on perClass Mira, allow me to take a second to show you how we can build a classification model in perClass Mira. Not only can we gather data, classify that data, but we can then deploy that classification model in real time. We're going to be using today the MVC V-near sensor. You can note it's quite compact design, but it's still very powerful and able to gather spectral data from a range of 400 to 1,000 nanometers. To simulate what you might be deploying our MVC V-near or other systems on, we have a small conveyor belt with some pieces of plastic fish with an illumination device as well. So I'm going to be going to the perClass Mira software and showing you how we build and deploy those classification models. Now we're going to build a classification model in the perClass Mira software and see it deployed in real time. First, we're going to start with a scan. Here we have a scan of some of the plastic fish samples we saw earlier. We're going to create some different classes. Class for the background, a label,
Some samples we're going to label as good and some samples that we're going to be labeling as bad. To label these different classes, we're going to paint the pixels of interest within the scene and match them to that particular class. As you can see, I've painted some of the pixels of the background blue, the good fish green, and some of the bad fish samples red. We then can click Model Search, and the perClass Mira software will find a model, and then we'll employ that model onto this image that we have on the screen. It will make a classification for each of the pixels in the scene. Furthermore, the perClass Mira will be able to find contiguous regions of similar pixels and label them as objects. Both the decisions and objects can be displayed in real time. Here we have some of those plastic samples of fish moving by, and we can see that the perClass Mira software identifies the different pixels in real time and assigns them to the different classes, but also can find objects within the scene and classify them in real time as well.
All right, now we're going to have our Q&A session. So anyone has any questions, please post them in the questions area. So we'll start with, would this work for fish other than tuna?
I can take that one. And I also just want to note this graphic on the background of the Q&A section are the per pixel regression classifications of all the tuna steaks that were measured during this product or during this project. And so you can see all of the different tuna steaks that we measured and their per pixel classifications here. So please enjoy that image during the Q&A session. So to answer the question, could this work for other fish? Yes, in general, you could create a model for another fish, specifically say another fish that is prone to develop histamine content. The careful thing to note is that, again, hyperspectral imaging is an indirect measurement that requires, or that's showing a correlation between the hyperspectral data and the measured result. And so a specific model would need to be made for whatever other target you want to measure. So a tuna model would not work for salmon or grouper or another fish. You would need a model specific to that raw fish. And I guess just to go one small step further, this was a raw tuna model. This would also not work on cooked tuna. Because again, once you cook the tuna, you're going to greatly change the spectral signature of that tuna, and the model was built on correlating to measurements of the surface of raw tuna.
What is the max line rate in hertz of your hyperspectral imaging sensors at full spectral and spatial resolutions?
So that depends on the sensor. So for the full spectral and spatial resolution of the Veneer sensor, I believe it is 400 hertz. The MVC near, I guess I know that it's faster than that. I don't have it off the top of my head, but you could find all that information on our website or on our data sheets. I would just also like to note that the most important thing isn't necessarily how fast the sensor can go at full spatial and spectral resolution, but how fast the sensor can accomplish your task. So for most of these final deployed solutions, we're not using the full spectral range of the sensor, and we can often optimize it to be a truncated spectral range that can operate at faster frame rates. And of course, there is some computational overhead required for deploying a model. So it's important to know the deployed speed of the final solution, And Headwall is very happy to work with customers to help you develop a solution end to end, and help you develop a model that will work at your required speeds for your required spatial resolutions. And so if you have a specific application in mind, please contact us, and we will do our best to serve your needs.
How would packaging like shrink wrap affect the results?
I can take this one. So the benefit of using hyperspectral imaging is that we can, of course, scan the scene if there was shrink wrap on the tuna. But the important thing to remember is that this particular model that we built was built for raw tuna that didn't have any shrink wrap over the tuna itself. So if you were to try to employ this current model, you likely wouldn't have any good results. But the beauty of it is that if you were to create a model with shrink wrap and you were still to ground truth the tuna, to use the chemical assays to determine the concentration of the histamine on the surface, you would still likely be able to build a very good regression model, just like we did with this study as well.
Can you train a model from multiple images, or do all classes and objects have to be present in one image for training?
No, you can train from multiple images. In fact, this model was created from multiple images. So you can load any number of images into perClass Mira simultaneously, and you can assign regression values per object on each image. So you could have one image with many objects, you could have many images with many objects, or you could have many images with one object each. All of those ways of collecting data are compatible with perClass Mira and can be used to develop a regression model.
What is the lowest ppm it can detect?
So we can't answer that question. In this particular case, we measured tuna anywhere from the range of, say, 10 to 15 ppm up to 200 ppm. But we did not do careful robustness testing to know just how accurately it can measure all of those ppm levels. And so I guess maybe a slightly different question would be, how precisely could it measure the parts per million of histamine? And again, so this model could produce results all the way down to 0 ppm. It would just predict that the results are 0 ppm. And how precise that answer is, it would require a bit more robustness testing. But based on our early results, we were correlating quite strongly to our ground truth. And that's, of course, another important thing to note is that the accuracy of our indirect method is limited by the accuracy of our ground truth. And in this case, we took one bit of tuna from a whole tuna steak and used that to assign a uniform histamine level for that entire tuna steak. A follow-up study could be done where we measure a tuna and then take multiple samples from that and train based on multiple different localized regions to possibly create a model with higher accuracy or higher precision. But again, so on a baseline level, we can confidently say that we can group these tuna steaks into low, medium, and high histamine levels, but we are getting very strong correlations. And so with a little extra effort, we can probably measure the histamine levels in tuna quite accurately.
If you had taken near range 900 to 1700 nanometers, would the result of regression been better?
Again, that's very hard to speculate. There's a chance that they could have been better, but I guess I'll say that these results in the Veneer spectral range were pretty darn good. And so usually if the results in the Veneer are good enough, there's often not a high motivation to move to the near, because of course the near is a slightly higher price point. The detector technology is a bit more expensive, so if you can accomplish something in the V near, usually you prefer that. Also, we were highly confident that we'd be able to correlate the visible spectra to the histamine level, so there's a chance that it would not be better. So we would need to do that test in order to find out for sure.
What is the power of the light source?
So our standard light source uses a 150 watt quartz tungsten halogen bulb focused down to a line using an aluminum reflector. I would need to look into exactly what light source was used for this particular set of data, but it would have been something on the order of the power of that light source.
Why is the histamine classification so speckled?
I think I can take this one, Will. So this is a nice, this is a great question because it helps show the differences between the many different applications that you can use the perClass Mira software for. When we were looking at the RGB classification images of the tuna steaks themselves, what we were looking at initially was the pixel by pixel classification, and those images were rather speckled. But then when we switched to the objects view, it was looking for, again, the contiguous region of the same classification of just tuna steak, and that's why those images were contiguous. But here in the regression model of the perClass Mira software is, again, doing similar to that classification of just each pixel. It's going pixel by pixel, making a decision on the regression, which is why it's particularly speckled. And it's also probably a good indicator that of the quality of the model as well, considering that the histamine distribution on the steak is not uniform, as Will mentioned before.
Regarding model deployment, the hyperspectral data is of high dimension. How to process real-time hyperspectral data?
Thank you very much for that question. So the way that the software works is every time we get a frame of data that's a spatial spectral frame, the model will process that spatial spectral frame and reduce it down to the classification values. And as the tuna or as the scene continues down the line, when an object is finished, it will use the buffered data to assign a regression value to the full object. So all of this can happen as fast as the frame rate of the sensor in most cases. And so perClass Mira is very powerful in that it can create these classification and regression models that given proper computing power, so usually we're using GPUs in the background and a fair amount of horsepower on our computers to get it done, but we can process a full frame of data generally about as fast as you can acquire data in the hyperspectral imager. So we can reduce the dimensionality and produce a result in real time, and usually that the standard result, say for the tuna, would be what we would call an object table. And so while we can output an image like this or a classification image, we would often just output a table that gives you the location of the object, and in this case, its regression value. And so that would contain all of the actionable information you need to make a decision or to command a robot. And it reduces the data stream by a lot. And again, this can all happen in real time. And any more precise answer than that would, again, depend on your precise model and application needs. And we're, of course, very happy to work with anybody on developing a specific application.
Can you share example spectra that were used to measure the histamine levels?
I don't have those available right now, But we could look into making some of these data cubes publicly available. So the way this, again, what this was done all in perClass Mira, and so the data cubes were loaded into the software package, the training was done, and then perClass Mira pulled spectra from all of the trained objects in order to train the regression model. And so I could provide the data cubes that were used to generate the model, and I could possibly provide the perClass Mira project file as well if you wanted to peruse the project file that was used. Of course, you would need either a license or a trial license of perClass Mira to browse that project file. And again, if that is something that interests you, please either contact Headwall or perClass to get a trial license or to request that data.
Thank you, everybody, for such great questions. We'd just like to let you know that coming up, the Seafood Expo Global in Barcelona is April 25th to 27th at the Fira Barcelona Gran Via venue in Spain. This is the world's largest seafood trade event. Buyers, suppliers, media, and other seafood professionals from more than 160 countries attend, and you can visit us at booth 3QQ02. And thank you so much for attending. We'd like to thank our presenters, Will Rock and George Killian again, and I hope everybody has a fantastic day.